Let's look at the Las Vegas skyline. Among the massive hotels and casinos, there is a relatively new structure that completely dwarfs its immediate surroundings. Inside that geodesic dome is a 160,000 square foot LED screen. To fill a continuous canvas of that size, you need a native resolution of 16,000 by 16,000 pixels. That is a 256 million pixel display. You cannot simply buy better off-the-shelf cameras or thicker cables to run something that large. To make this venue work, engineers had to abandon standard filmmaking technology and build an entirely new ecosystem from the ground up. The industry standard way to shoot giant format immersive video is to rig a bunch of high-end cinema cameras together and stitch the images together in post-production. Early prototypes for this project welded roughly a dozen cameras into a single unit, weighing up to 300 pounds. A rig that heavy is a nightmare to transport and nearly impossible to mount in tight spaces. Worse, blending all those different lenses created visible optical seams in the final image. Then there was the data problem. Even if the optical seams were fixed, trying to force a single, uncompressed 16K data stream through standard broadcast cables would immediately overwhelm the infrastructure. Pushing traditional hardware to be bigger and heavier hit a hard physical wall. To achieve 16K capture and playback, the engineering team had to design a custom workflow from scratch to conquer 3 specific bottlenecks: capture, throughput, and playback. The capture bottleneck was solved by building a single camera from scratch, the Big Sky system. At its core is a custom sensor developed in partnership with ST Microelectronics. It's a 316 megapixel die that shoots in an 18K square format. The Big Sky chip provides 7 times the surface area of a standard cinema sensor. This 18K footprint creates a buffer to digitally stabilize footage without losing 16K quality. Custom 150-degree fisheye lenses then project a circular image perfectly inside the square, eliminating wasted pixels. Combining those circular optics with a giant square sensor delivered enough resolution in one shot to eliminate the need for heavy multi-camera rigs. But a 316-megapixel sensor creates a massive new problem. How do you move that much data off the camera head without dropping frames? The camera head produces a 500 gigabit per second data pipe. That feed travels over fiber optics to a dedicated media recorder, instantly writing to custom 32 terabyte magazines at up to 50 gigabytes per second. The sheer volume of raw data meant standard off-the-shelf editing tools couldn't even open the files. The studio had to build a proprietary GPU-accelerated software pipeline just to read and manage the footage. That brings us to the final bottleneck: getting the finished 16K footage onto the massive LED canvas in real time without melting the rendering machines. The ultimate stress test for this playback system came during the venue's opening residency, featuring U2. The production team knew a single supercomputer couldn't handle the load. Instead, they relied on a swarm of parallel processing. Built by production company Disguise, the master 16K video file is automatically sliced into 23 manageable pieces. Each slice is distributed to its own media server. Instead of one machine struggling with a 256 million pixel canvas, 23 separate servers each output standard 4K streams. To transport these streams across the building, they bypassed standard point-to-point video cables. Instead, they used SMPTE ST2110, which is an IP-based broadcast network standard. Dividing an impossible mathematical load into dozens of smaller, synchronized IP streams made real-time 16K playback a reality. Curious, with 23 different servers handling separate pieces of the video, you might expect to see seams or out-of-sync frames on the dome. They stay aligned because the software orchestrates everything using musical beats, bars, and precise timecodes. Every parallel stream shares a common timing reference over the IP network, locking all 23 servers onto the exact same frame. That identical master clock also controls the venue's audio system. The sound is driven by 167,000 individually amplified holoplot speaker drivers, hidden completely behind the LED screen. Because the audio and video share the same IP network and timecode, the system uses 3D audio beamforming to steer distinct sounds directly to specific physical seats, perfectly synchronized with the visuals happening above. By breaking a continuous 256 million pixel canvas in perfectly synchronized parallel streams, engineers bypass the physical limits of traditional filmmaking. The venue pushes 160,000 square feet of live visuals and thousands of distinct audio channels simultaneously, without dropping a frame. The Sphere proves that massive digital experiences are built on brilliantly choreographed swarms of technology, rendering the hunt for a single, all-powerful supermachine obsolete.